So our final speaker for the break is Shiyue Li, and she's going to talk about K-rings of wonderful varieties and matroids.
So I work in the field of algebraic geometry and combinatorics. So there's a lot of interplay between these two fields. So in algebraic geometry, I mainly think about moduli space of curves, and examples of such things are, say, the compactification of Riemann surfaces with genus G and some other variations. And in combinatorics, examples that I think about are, say, graphs and matroids. And I go from algebraic geometry to combinatorics mainly via the way of tropical geometry. And I go from combinatorics to algebraic geometry using many different ways. So today I want to tell you one example of such an interplay. So let's go back to a very general setting where I want to think about a smooth projective variety. You can think in your head as something like this blob on the right, this thing. And this thing might carry something called a vector bundle. And you want to consider this structure that governs all the vector bundles on X and form an algebraic structure that's called Grothendieck group of vector bundles on X. And it's generated by the isomorphism classes of vector bundles on X, modulo the relation of F being equal to E and G whenever the vector bundles E, F, G form short exact sequences like this. So this is a group, but you can also impose a ring structure on this by setting the class of structure sheaf on X to be 1 and take products of two classes to be the class of tensor product, to be the class of tensors of these two vector bundles. And this will give you a ring structure. And alternatively, you might consider something called a Grothendieck group of coherent sheaves, which is defined similarly. But there's a theorem in classical algebraic geometry that's called Hilbert-CCG's theorem that tells you, because of our condition of X being smooth, these two structures are actually the same. And I will denote this structure as K of X for the rest of the talk. And people have thought about this for a very long time. In 1954, Hilsberg proved something that's based on classical results of Riemann and Roth that relate this structure to a classically known structure called the Chow ring of X. So let me remind you. So the Chow ring is a structure that governs all the subvarieties of X, isomorphism classes of, modulo some rational equivalence relation. Morally speaking, this means if you have a subvariety or two subvarieties, distinct varieties, if you can drag one along a P1 and it turns into another one, you can interpolate them via a P1 family, then you consider them as equivalent, morally speaking. And here's where Riemann-Roth says these two are actually isomorphic after tensoring with Q. And the isomorphism is called Chern character that sends a class of a line bundle to the exponentiation of this line bundle. And more, that there's a map from the K ring to the ground field Q by taking, for each vector bundle, the alternating sum of the dimension of the sheaf cohomology of that vector bundle. And you get a number. On this side, that you can also obtain a number by taking the degree of the Chow ring, which is pushed forward to a point. And Herzberg-Riemann-Roth says that if you compute the Euler characteristic of this of a vector bundle, that number is equal to you first send to the result when you first send that vector bundle via the Chern character, then intersect it with some canonical class associated to the variety X, which is called the top class, and the result will be the same. So here's an example in the case of P2, projective plane. So on the left-hand side, let me just give you the K ring, which is a polynomial ring generated by O of 1, modeled by some relations. And on the right-hand side, I also have a polynomial ring generated by the class of a hyperplane, modeled by the relation that the hyperplane intersect by itself 3 times exceeding the dimension, it vanishes. And so the Chern character wants to send the class of O of 1 to the exponentiation of the first Chern class of this O1, which is H, and the result will be this. So let's execute Hesper-Rimmer in this example. So for any monomial, the Euler characteristic is computed as this number. Monomial meaning this is my generator, so this to the n is a monomial in this ring. And this number has a combinatorial interpretation, which is the number of lattice points in the nth dilation of the standard polytope inside of R3. Here I've drawn two examples in m equals to 1, so you count 3 points, and then m equals to 2, you get this polytope, and you count 6 points, and that's satisfying this formula. And on the right-hand side, if I do the Chern character together with intersecting with the top class, I get this number times h squared. And the degree of h squared, namely, if you take two hyperplanes intersect them, you should get a point, and you just get this number, and then you simplify and verify that these two numbers are the same. So this is a classical theorem. But in general, this participant of this formula, which is the top class, is really hard to compute, and the complexity increases as dimension of the variety increases. So, and furthermore, also, we would like to ask, is there a relation between the complicated K ring and the probably better known Chow ring that kind of avoid the top classes, which is hard to compute, and also avoid, say, passing to a different ground ring. And if so, we might know, we can compute an integral K ring if we already know an integral Chow ring, and we can also compute the Euler characteristic in an easier way. And we answered this, we gave an affirmative answer to this question in the case of wonderful varieties of realizable matroids and for Tor varieties of matroids. And this is joint work with Matt Larson, who's here, Sam Payne, who's here, Nick Propo, who's not here. And prominent examples are Deligne-Mumford compactifications of moduli space of curves in genus 0 and variations. So let me introduce you the main player or the main ingredient of this geometric result. So the main player is this variety that's called wonderful compactification of the complement of a hyperplane arrangement. And this is introduced by Di Concini and Percesi in 1995. And I'll give you the definition along with an example. So let's start with the vector space L over any field K. And here on the right, I've drawn the projectivization of a three-dimensional space. So it's a plane. And a finite set of hyperplanes intersect only at the origin, which is denoted as A. And the indexing set will be called capital E. So here I have 4 hyperplanes lying in this plane like this. And now I can define some functions on subsets of these hyperplanes. So for each subset of the ground set, I look at the intersection space of all the hyperplanes. And the rank of the subset S will be the dimension of the quotient space of the intersection space. And a flat, which is a thing, is a subset F that's maximal among its rank. And don't worry, here's an example. So let's compute this. So the rank of the empty set will be always 0 because you're quotienting out everything. And if you take a single hyperplane and you look at the dimension of the total space, which has dimension 3, and multiply by the dimension of the hyperplane, which has dimension 2, you get 1. So the rank of any singleton thing will be 1. And dimension of any tuplet, so will be, first of all, let's observe that every tuplet intersects at a point. So the dimension will be 0, it would be 1, and 3 minus 1 will be 2. So rank of tuplets will be 2. And for 3 sets, there will be 2 situations. First is 1, 2, 3 do intersect only at a point. So the rank will be 3 minus 1, which is equal to 2. And in other cases, 3 things always intersect trivially. So the rank will be 3, which is 3 minus 0. And 1, 2, 3, 4 all intersect trivially. So the dimension will be 3 minus 0 equal to 3 again. So you can observe that 1, 2, so the maximal sets that are maximal among its rank, the sets that are maximal among its rank will be these things. And in particular, 1, 2 is not a flat because it has the same rank as 1, 2, 3 and is contained in 1, 2, 3. So the set of all flats actually form a geometric lattice. And this hyperplane determines something called a realizable matroid. And in general, you can extract this rank function from this kind of computing dimension sort of business and give axioms of matroid like this. So a matroid is the data of a ground set together with the rank function from the power set of the ground set to non-negative integers such that rank of empty set is 0, rank of 2 sets always satisfy this condition called self-modularity. And whenever you augment the rank, augment a set and the rank behave like this. And there's a result that says almost all matroids are not realizable. So in the space of matroids, the realizable matroids are vanishingly small. Okay, but a lot of information can be known, or behaviors can be known from the case of realizable matroids by studying the geometry of these hyperplanes. So then there exists a rational map from the projectivization of the vector space into this huge product of the quotient space for each flat. And the wonderful variety of this hyperplane arrangement complement will be the closure of this image of the plane under this map. And this is very complicated, but what it's actually doing is something called a blowup, which is a modification of the boundary of the hyperplanes such that all the places that are the linear subspaces are modified to become something called simple normal crossings. Namely, they look like hyperplanes or coordinate hyperplanes intersecting. So this object is very well studied, and Wagner-Uzvinsky in 2004 studied the Chern of this object, giving these generators and relations. And June and Eric Katz in 2012 proved the log concavity of chromatic polynomials of graphs, and furthermore, characteristic polynomials of realizing matroids. And Di Persito and June and Eric Katz in 2018 proved the log concavity of characteristic polynomials of all matroids using ideas inspired from the geometry of this object. And it also played a role in the proof of top-heavy conjecture of matroids by Tom Broughton, June, Jacob Mothern, Nick Proudfoot, and Bo Tong, who's also here. But to say the punchline, I want to say that there is an alternative presentation of the Chern, which is given by Beckman, Chris and Connor Simpson, who's also here. And it's generated by some really nice generators of really nice classes in the Chern that have very elegant intersection properties. And so to say our main theorem, which is a replacement of Herzberg-Riemann-Roch, I want to let X to be the wonderful compactification of a complement of a hyperplane arrangement, which you can think just using moduli space of curves as an example. And for each flat F, I want LF to be the pullback of O1 to the wonderful variety from this product, because for each factor, I can pull back an O1. And then there exists an isomorphism from the integral K ring to the integral Chao ring that's different from the Chern character that sends 1 minus the dual class of this line model that I just defined to the generators, the set of nice generators that I just gave you. And now both of these rings have maps to the integers, and I can still compute the Euler characteristic on the left-hand side. But on the right-hand side, instead of sending a vector bundle through the Chern character, I will send it from this alternative, via this alternative map, and then intersect it with this simpler looking polynomial. And we prove that the computation of these two numbers will be the same. So this is a replacement of the Chern character and also avoid the passing to the rationals, namely, yeah. So the key idea is to anchor the geometry of this wonderful variety in this product of projective spaces, which we have better hope of understanding. And I would just say the key observation, which is already, so the key phenomena that's stated in the theorem already happens in projective spaces. So for projective spaces, there is already a ring isomorphism that replaces the Chern character. So it sends not the O1 of the projective space, but the structure sheaf of a hyperplane to the class of a hyperplane. But let's compare that this is different from the Chern character. So what the Chern character wants to do is sends the class of structure sheaf, which is written like this, to 1 minus the exponentiation of the first Chern class of O1, which turns out to be, sorry, O of minus 1, which turns out to be minus h, and then the result will be this thing rather than the class of a hyperplane. So it is already different from the Chern character. And then you see what happens when you restrict this map to the wonderful compactification. So this is just and then you also verify that on projective spaces, this formula holds, and see that this whole computation descend to the wonderful compactification. So we got inspired from two special cases, namely the Permutohedra variety, which is also a very combinatorially rich variety, and the Stellahedra variety, but they use torque equivariant localization results, which are not available for general matroids or realizable matroids. And this result has, as I said before, applications to Deligne-Mumford compactifications of genus zero curves and variations, which are realized by these two papers as wonderful compactifications of certain matroids. So I guess my question for the audience is, what other spaces enjoy this property? So I got some questions last year from some topologists, but I'm not able to solve them because I'm not a topologist. So yeah, thank you very much.
Thanks. Questions?
What's a good smooth projective variety whose Kering and Chong are not isomorphic?
Integrally, probably something that you can easily cook up torsions. I don't know off the top of my head.
You take a flag variety over somewhere the group is not special somehow integrally the cohomology might not be checked. I mean, not the flag. The integral cohomology is not always generated in degree 2.
Three-dimensional quadratic hypersurface.
Okay, which one has torsion?
They don't have torsion, but it's not the cohomology isn't generating the degree 1. Degree 2. Special case.
In the examples that you have, does this, sorry, what symbol is that? S?
Zeta.
Zeta, sorry. Does zeta always have the property that it takes O of a subvariety to that subvariety? Like in the projective space example?
In the Kering, sorry, in the wonderful compactation, no. Yeah.
When you say wonderful variety, is it for the maximal building set or for any choices?
Yeah, we proved this for maximal building set, but the proof should go through arbitrary building set.
So you expect one of these exceptional HRRs for all building sets?
Sorry?
So you expect an exceptional HRR for all building sets?
Yes. And also I didn't show you the statement for torque varieties of arbitrary matroid. So yeah, for arbitrary matroid, you can also talk about this, but you work with the torque variety of the Berman head instead.
Is it also true for the other kinds of discontinuous portrays a wonderful compactification of like?
I don't know. Yeah, so I don't know about this other wonderful compactification. Much.
Of groups?
Yeah,
Of symmetric spaces and groups.
we don't know that much about.
There are no more questions. Let's thank Shiyue again.